What if everything you thought you knew about our solar system was wrong? Those neat textbook diagrams, perfect circles, flat orbits, a yellow sun sitting still at the center, are comforting but misleading. The truth is far more chaotic. So, if you want to know the real truth about the solar system, then watch this video till the end and subscribe to the channel. Let's begin. Let's start with one of the most common misconceptions: the idea that all the planets orbit the Sun on the same perfectly flat plane. School diagrams make it look that way: a clean, horizontal disk with planets circling neatly like rings on a record. It's simple, it's tidy, and it's completely misleading. In reality, our solar system isn't flat at all. Each planet's orbit is tilted at a slightly different angle relative to an imaginary baseline called the ecliptic plane, the plane of Earth's orbit around the Sun. Mercury, for example, is tilted about 7 degrees from that plane. Pluto, before its demotion, was even more extreme, orbiting at a wild 17-degree angle. Even the giant planets, which seem to align closely, have subtle variations that make the solar system a dynamic, three-dimensional structure rather than a smooth disk. These inclinations mean that, at any given moment, the planets aren't truly lined up in a straight path. They weave above and below the ecliptic, like cosmic dancers in a spiraling performance. And here's where it gets even more fascinating. Those orbital tilts aren't fixed. Over millions of years, gravitational tugs from other planets, passing stars, and even remnants of ancient collisions cause those angles to shift. The solar system, then, isn't a rigid clockwork. It's a constantly moving, breathing 3D ballet of worlds, each pulling and nudging the others in subtle ways. The truth is, space isn't flat. It never was. And once you realize that, the rest of what we've been taught about our perfect solar system starts to unravel. Because if the orbits aren't circular and flat, what else isn't as it seems? We've always pictured the planets moving in perfect circles, smooth, even paths carved around the Sun like tracks on an invisible racetrack. It's the way most schoolbooks draw it, and it feels right, clean, balanced, predictable. But in truth, not a single planet in our solar system travels in a perfect circle. Every orbit is elliptical, stretched slightly like a cosmic oval, and constantly changing under the subtle but relentless pull of gravity. This idea goes all the way back to Johannes Kepler, who shattered centuries of belief when he discovered that planets follow ellipses, not circles. Earth, for example, is about 5 million kilometers closer to the Sun at its nearest point, called perihelion, than at its farthest, aphelion. That's not much in cosmic terms, but it changes everything. The shape of these orbits means planets speed up when they're closer to the Sun and slow down as they move away. The elegant, circular simplicity we imagine is really a delicate, gravitational dance. And those ellipses aren't fixed either. Over long timescales, they shift. They twist, stretch, and wobble due to the gravitational influence of other planets, the pull of the Moon, and even the passing tug of distant stars. Jupiter, with its immense mass, exerts a particularly powerful influence, subtly reshaping the paths of neighboring worlds. The result? A solar system in perpetual motion, where no orbit is ever truly the same twice. So when we picture those tidy circular lines around the Sun, we're really looking at an illusion of order superimposed on a reality of constant motion. The orbits aren't perfect, and that imperfection is what makes our solar system alive, a living mechanism, always in flux. And once you realize that the planets don't travel in flawless circles, it's only natural to wonder, if their paths aren't perfect, could the Sun itself be perfectly still? We were all taught to think of the Sun as the anchor of the solar system, the unmoving center around which everything else revolves. It's comforting, right? The idea of a fixed point holding the chaos together. But here's the truth that most people never stop to consider. The sun isn't stationary at all. It's racing through space at breathtaking speed, dragging every planet, moon, and asteroid along with it in a vast cosmic journey. Our entire solar system is orbiting the center of the Milky Way galaxy at roughly 230 kilometers per second. That's nearly 500,000 miles per hour. In the time it takes you to blink, the sun has already moved dozens of kilometers through space. It takes about 225 to 250 million years for the sun to complete a single orbit around the galactic center, a trip so immense that it's made the journey only about 20 times since the solar system first formed. And here's where the real mind-bender comes in. Because the sun is moving, the planets don't simply orbit it in flat circles like on those neat classroom models. Instead, they follow it in spirals, each one tracing a looping helical path through space. Picture the sun as a comet, blazing through the galaxy, with the planets swirling and weaving behind it like glowing ribbons in a cosmic current. It's a 3D dance across unimaginable distances, dynamic, alive, and in constant motion. Even the sun itself isn't still within its own body. It wobbles slightly because of the gravitational pull from the planets, especially massive Jupiter. This subtle motion causes the sun to orbit around a shifting center of mass, called the barycenter, that sometimes lies just outside its surface. So technically, even within our solar system, the sun isn't the true center. So no, the sun doesn't sit motionless in space, ruling from the middle like a king on a throne. It's more like the leader of a caravan, guiding its planets, moons, and asteroids through the galaxy in a vast, spiraling voyage. And if even the sun moves, it makes you wonder, are the planets really as independent as we think? We like to imagine the planets as isolated travelers, each minding its own path around the sun, solitary wanderers gliding in their perfect orbits, untouched by one another. But that's a comforting lie. In truth, every planet in our solar system is part of a vast web of gravitational influence, constantly tugging, nudging, and reshaping each other's fates. The solar system isn't a collection of independent worlds. It's a tightly woven gravitational ecosystem, and one planet in particular, Jupiter, is its undisputed heavyweight. Jupiter's mass is staggering, more than twice that of all the other planets combined. Its gravitational pull doesn't just keep its moons in check, it sculpts the structure of the entire solar system. The asteroid belt, for instance, exists largely because of Jupiter. When the solar system was forming, there was enough material between Mars and Jupiter to create another planet. But Jupiter's immense gravity kept those rocks from coalescing, stirring them into chaos and leaving behind the broken remnants we now call asteroids. Jupiter also acts as both protector and disruptor. Its gravity deflects or captures countless comets and asteroids that might otherwise strike the inner planets, including Earth. Without Jupiter, the early solar system might have seen far more catastrophic impacts, possibly preventing life from ever gaining a foothold here. Yet at the same time, that same gravitational might can sling dangerous objects inward, turning it from guardian to occasional threat. Even the orbits of the other planets aren't immune to these invisible forces. Over millions of years, small gravitational tugs between planets subtly alter their orbital shapes and tilts. Saturn's gravity interacts with Jupiter's, creating resonances that ripple through the solar system like invisible waves. These delicate gravitational dances have long-term consequences, shaping climates, influencing asteroid trajectories, and even affecting the rhythm of Earth's ice ages. So the next time you picture the planets as independent spheres drifting in peace, remember this: every movement, every orbit, every delicate balance in the solar system is influenced by unseen gravitational threads linking one world to another. The planets are not separate travelers. They're partners, in an ancient, ever-changing dance. And speaking of partners and planetary status, there's one world whose relationship with the rest has sparked more debate than any other: Pluto. The story of Pluto is one of the most emotional chapters in modern astronomy, a tale that reveals as much about our human need for order and identity as it does about science itself. For decades, Pluto sat comfortably as the ninth planet, the tiny but proud outpost of our solar system. Generations of students grew up memorizing its name at the end of that familiar planetary list: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. But then, almost overnight, Pluto was demoted, stripped of its title, and reclassified as a dwarf planet. The reaction was immediate and passionate. People protested, scientists argued, and memes were born. How could we just decide that a planet wasn't a planet anymore? Was Pluto unfairly kicked out of the family? To understand the truth, we have to look at the messy process of how we define a planet, a process that, surprisingly, wasn't clearly established until Pluto forced astronomers to confront it. When Clyde Tombaugh discovered Pluto in 1930, it was immediately hailed as the ninth planet. But even then, astronomers had doubts. Pluto was small, incredibly small. Its diameter is only about 2,376 kilometers, which is roughly 2/3 that of Earth's moon. Over time, as technology improved and new telescopes scanned the outer solar system, astronomers began finding other icy bodies beyond Neptune that looked strikingly similar to Pluto. One in particular, discovered in 2005, was Eris, an object nearly the same size, and in some ways even more massive than Pluto. That discovery triggered a crisis. If Pluto was a planet, then Eris should be one too. But if both were planets, what about the dozens of other large icy objects that astronomers were beginning to find in the same region? The Kuiper Belt. By that logic, the solar system could soon have hundreds of planets. Clearly, something had to be redefined. So in 2006, the International Astronomical Union, IAU, made a bold and controversial move. It officially defined what a planet is. According to the IAU, for an object to be considered a planet, it must meet 3 criteria. 1. It must orbit the Sun. 2. It must be massive enough for its gravity to pull it into a nearly round shape. 3. It must have cleared its neighborhood of other debris, meaning it has become gravitationally dominant, sweeping up or ejecting smaller objects near its orbit. Pluto failed that third test. It shares its orbital zone with countless other icy bodies in the Kuiper Belt, meaning it hasn't cleared its path. So, by this new definition, Pluto was reclassified as a dwarf planet, not because it was unworthy or insignificant, but because it didn't fit the scientific criteria. Now, here's the fascinating part. The decision wasn't just about Pluto. It was about us. It forced humanity to confront how we define categories in a universe that doesn't care about our labels. The cosmos doesn't draw lines between planets and non-planets. We do that to make sense of an overwhelming reality. Pluto's reclassification wasn't a punishment. It was a step toward refining our understanding of what a planet truly is. But that didn't make it any easier emotionally. People felt betrayed. Pluto wasn't just a cold rock at the edge of the solar system. It was part of our collective imagination. It represented mystery, distance, the little outsider that still belonged. And when scientists told us it didn't count anymore, it felt like someone had rewritten our childhood sky. What's even more intriguing is that, despite its demotion, Pluto became more fascinating than ever. The New Horizons mission, which flew by Pluto in 2015, revealed a world far more complex than anyone expected. Mountains of ice, vast nitrogen plains, possible subsurface oceans, and even signs of geological activity. It wasn't a static frozen rock. It was a living, evolving world with its own story to tell. In many ways, Pluto's fall from grace sparked a new golden age of exploration. Its downgrade led to the discovery of entire populations of dwarf planets: Eris, Haumea, Makemake, Sedna, all of which helped us understand that our solar system doesn't end with Neptune, but stretches far beyond into a vast icy frontier. So was Pluto unfairly demoted? Emotionally, maybe. Scientifically, no. In fact, Pluto's reclassification might be one of the best things to ever happen to planetary science. It forced us to look outward, to reconsider our definitions, and to embrace complexity rather than cling to nostalgia. It reminded us that science isn't about preserving comforting truths, it's about seeking deeper ones. The Pluto controversy also reveals something profound about our relationship with the cosmos. We crave neat categories and clear hierarchies, but the universe resists that simplicity. It's messy, ambiguous, and full of grey areas. Pluto exists in that grey area. Small but mighty, demoted but beloved, redefined but not forgotten. And if Pluto's story taught us anything, it's that the edges of our solar system are far from empty. In fact, that brings us to another great misconception, one that shapes how we imagine the space between worlds. Because if Pluto revealed that the outer solar system is crowded with hidden objects, maybe the space between the planets isn't as empty as we've been led to believe. When we think of the space between planets, we tend to picture an endless void, a black, silent nothingness stretching across billions of kilometers. The images we've seen in documentaries or school textbooks reinforce this illusion. Planets floating like isolated marbles in a vast, empty sea. It's a poetic image, tranquil, minimalist, and comforting in its simplicity. But it's also a lie. Space, even the so-called empty regions between planets, is anything but empty. It's a churning, invisible ocean of energy, dust, particles, and magnetic fields. What appears to be still and silent is, in truth, an active environment constantly alive with motion, radiation, and unseen forces. The space between the planets isn't a void. It's the living tissue that binds the solar system together. Let's start with dust. Tiny particles smaller than grains of sand, left over from the formation of planets and the disintegration of comets and asteroids. These motes drift through the solar system, reflecting faint sunlight and forming what we call the zodiacal cloud. If you've ever seen a faint, hazy glow on the horizon just before dawn or after dusk, a mysterious light that seems to stretch upward along the zodiac, that's sunlight scattering off this interplanetary dust. It's a subtle but beautiful reminder that space is never truly empty. It's filled with the leftovers of creation. Then there's the solar wind, a relentless stream of charged particles, mostly protons and electrons, constantly flowing outward from the sun. This wind fills every corner of the solar system, shaping planetary atmospheres and sculpting the long tails of comets as they approach the sun. Earth is shielded from most of it by our magnetic field, but when those charged particles collide with our atmosphere, they create one of the most breathtaking spectacles in nature, the auroras. What we see as shimmering curtains of green and purple light are actually the fingerprints of the sun's invisible breath interacting with our magnetic defenses. Speaking of magnetic fields, the solar system is full of them. The sun's magnetic field stretches far beyond Pluto, twisting and folding in on itself as the sun rotates. Each planet contributes its own magnetic bubble, a magnetosphere, which interacts with the solar wind in unique ways. Jupiter's magnetosphere, for example, is so enormous that if we could see it with the naked eye, it would appear larger than the full moon in our night sky, even though Jupiter itself is hundreds of millions of kilometers away. These magnetic fields connect and clash, forming vast, unseen boundaries that define the real architecture of our solar system. And then there are cosmic rays, high-energy particles that stream in from beyond our solar system, accelerated by distant supernovae and galactic phenomena. These rays constantly bombard our solar neighborhood, passing through planets, spacecraft, and even us. Every square centimeter of your body is struck by thousands of them every second, though you don't feel a thing. They're a reminder that the solar system is not isolated. It's part of a larger cosmic ecosystem, open to the influences of the galaxy beyond. Even comets, those ancient wanderers, play a role in filling the empty spaces. Each time a comet passes near the Sun, it sheds material, leaving behind a trail of dust and ice. When Earth crosses one of these trails, the particles burn up in our atmosphere, creating meteor showers, brief, dazzling reminders of how connected everything in space really is. And yet, perhaps the most profound illusion of all is the stillness. We imagine the planets floating serenely, but the interplanetary medium, the space between worlds, is a turbulent, dynamic environment. Shock waves from solar flares ripple through it. Magnetic storms erupt and fade. Dust grains collide, charge and drift. In the vast expanse where our eyes see nothing, an invisible drama unfolds every second. Even the boundaries of our solar system blur into this cosmic sea. The solar wind eventually slows and merges with the interstellar medium, the thin gas and dust that fill the space between stars. That invisible frontier, called the heliopause, marks the true edge of our Sun's influence. When Voyager 1 crossed it in 2012, it didn't enter silence. It entered a different kind of sound, a place where the whispers of our star gave way to the faint murmur of the galaxy itself. So no, space isn't empty. It's alive, filled with matter, energy, and invisible structures that weave everything together. The void we imagine is, in fact, the greatest illusion of all. Between every planet, between every orbit, lies a vast field of interaction. A place where gravity, light, and magnetism never sleep. And once you realize that the nothingness between planets is teeming with unseen motion, another myth begins to crack. The idea that the planets themselves are smooth, perfect spheres drifting in that void. Because even the planets, those majestic orbs we see in photos, are not as perfectly round as we've been told. When we picture planets, we see smooth, flawless spheres, round, balanced, and symmetrical. Every diagram, every model, every globe we've ever held reinforces that idea. Planets, we're told, are perfect orbs spinning silently through space. But the truth is far more dynamic and far less perfect. Most planets aren't perfectly round at all. They're slightly squashed, stretched, or bulging in ways that reveal just how alive and energetic they really are. The reason lies in one simple force that shapes nearly everything in the universe: rotation. When a planet spins, centrifugal force pushes outward at the equator, opposing gravity's pull toward the center. The faster a planet rotates, the stronger that outward force becomes, causing the planet to bulge around its middle and flatten at the poles. This effect is called oblateness, and it's one of those hidden details that turns textbook simplicity into fascinating reality. Take Jupiter, for example. The gas giant is the fastest spinning planet in our solar system, completing one full rotation in just under 10 hours. That rapid spin makes its equator bulge dramatically. If you could look closely, you'd notice Jupiter isn't a perfect sphere. It's about 6.5% wider at the equator than from pole to pole. That might not sound like much, but for a planet with a diameter of nearly 140,000 kilometers, it means the equator sticks out more than 9,000 kilometers farther than the poles. In other words, Jupiter is noticeably squished. Saturn takes that distortion to an even more extreme level. Though it's slightly smaller than Jupiter, Saturn spins almost as quickly and is made mostly of hydrogen and helium, very light gases. The combination of low density and high rotation speed means Saturn bulges even more dramatically. Its equatorial diameter is about 10% larger than the distance between its poles. If you saw it up close, it would look more like a slightly flattened beach ball than a perfect globe. In fact, Saturn's shape is so distorted that it's visible even through medium-sized telescopes, a subtle but unmistakable sign of just how fluid and dynamic this planet really is. Even Earth, our seemingly perfect homeworld, isn't truly round. We call its shape an oblate spheroid, meaning it's slightly flattened at the poles and bulging at the equator. Earth's equatorial diameter is about 43 kilometers larger than its polar diameter. That bulge means gravity isn't uniform across the planet. You actually weigh a tiny bit less at the equator than at the poles because you're slightly farther from Earth's center of mass and moving faster due to the planet's spin. Other planets show their imperfections in different ways. Mars has a small equatorial bulge, evidence of its own rapid spin early in its history. Uranus, which rotates almost on its side, has an odd shape influenced by both its tilt and its internal structure. Even Neptune, though far from the Sun and slower spinning than Jupiter or Saturn, shows measurable flattening. And when we move beyond the planets to moons and dwarf planets, the story becomes even more complex. Some are elongated, lumpy, or irregular, shaped not by spin, but by their own incomplete gravitational pull. For instance, Haumea, one of the dwarf planets beyond Pluto, spins so fast that it's stretched into an ellipsoid, more like a cosmic rugby ball than a sphere. It completes a full rotation in just about 4 hours, one of the fastest in the solar system. That rapid spin distorts it so much that its shape alone tells the story of its turbulent past. These deviations from roundness might sound trivial, but they're deeply revealing. They tell us about each world's interior composition, rotation speed, and even gravitational history. A rocky planet's resistance to deformation says something about its density and core. A gas giant's extreme flattening reveals how fluid and dynamic its structure is. These bulges and distortions are, in a sense, the fingerprints of each planet's character, proof that these worlds aren't static spheres, but living bodies constantly shaped by motion, gravity, and time. And here's where the illusion becomes poetic. We often equate perfection with symmetry, as if being perfectly round makes something more celestial, more divine. But nature doesn't care about geometric perfection. The real beauty of the planets lies in their imperfections, their bulges, their tilts, their irregularities. They remind us that motion always leaves its mark, and that even in the vastness of space, nothing remains perfectly still or perfectly shaped. Even the Sun, the supposed perfect sphere at the center, isn't entirely round. It too bulges slightly at the equator because of its rotation, though the effect is subtle, only a few kilometers of difference across its massive diameter. It's a quiet echo of the same universal truth. In motion, perfection bends. And if even the planets and the Sun refuse to conform to perfect symmetry, what does that say about the boundaries of our solar system itself? For decades, we've been told it ends neatly at Pluto, that beyond it lies only darkness and emptiness. But that, too, is a comforting simplification. The truth is that our solar system doesn't end where we think it does. It stretches far beyond Pluto, into realms so vast and mysterious that we've barely begun to grasp their scope. For generations, we've been taught that Pluto marked the end of our solar system, the last lonely world circling the distant edge of the Sun's domain. School charts and science posters showed Pluto as the final stop, a tiny frozen speck completing the family of 9 planets. Beyond it, we were told, lies nothing but the cold emptiness of deep space. But that picture couldn't be further from the truth. In reality, Pluto isn't the boundary. It's just the beginning of a vast, hidden frontier that extends billions of kilometers farther, a region so immense that it blurs the very definition of where our solar system ends and interstellar space begins. Once you pass Pluto's orbit, you enter a region called the Kuiper Belt, a sprawling, icy wilderness that stretches from about 30 to 55 astronomical units, AU, from the Sun, 1 AU being the distance between the Earth and the Sun. The Kuiper Belt is like a second asteroid belt, but far larger and more mysterious. It's home to countless icy bodies, the leftovers from the early days of planet formation. Pluto itself is just one of these objects, albeit one of the largest and most famous. But it's far from alone. The Kuiper Belt contains a staggering number of objects, perhaps hundreds of thousands, that are larger than 100 kilometers across, and trillions of smaller ones. Many of them, like Haumea, Makemake, and Eris, are dwarf planets, sharing characteristics with Pluto. Others are ancient remnants, primordial building blocks of the solar system that never grew into full-fledged planets. Some follow stable orbits, while others are chaotic, tugged and scattered by Neptune's gravity. In fact, Neptune's gravitational influence is the reason the Kuiper Belt's inner edge is so sharply defined. Its resonances act like invisible walls that corral the icy debris into intricate orbital patterns. But the Kuiper Belt is only the first layer of the Sun's farthest dominion. Beyond it lies an even stranger and more distant region, the scattered disk. Here, icy bodies move on wildly elongated orbits, some stretching hundreds of astronomical units from the Sun. These objects are thought to have been flung outward by the gravitational push of Neptune and Jupiter billions of years ago, sent on eccentric journeys that take them from near the planets to the frozen reaches of deep space and back again. One such object, named Sedna, has an orbit so extreme that it never even enters the Kuiper Belt. Its closest approach to the Sun is about 76 astronomical units, and its farthest point may extend nearly 1,000 astronomical units. Sedna's orbit takes over 11,000 years to complete, and yet, even Sedna is just scratching the surface of what lies beyond. Farther still, in the deep, dark outskirts of our solar system, lies the most mysterious region of all, the Oort cloud. Unlike the flat, disk-like structure of the Kuiper Belt, the Oort cloud is believed to form a vast spherical shell surrounding the entire solar system, extending possibly as far as 100,000 astronomical units from the Sun. That's about 1.5 light years, or roughly halfway to the nearest star system, Alpha Centauri. If the solar system were the size of a city, the known planets would be huddled around a single block, while the Oort cloud would stretch all the way out to the suburbs. The Oort cloud is where most long-period comets come from, those icy travelers that swoop into the inner solar system every few thousand or even millions of years, flashing their bright tails before retreating back into the dark. These comets are like ancient messengers, fragments of the solar system's birth that have spent eons drifting at the very edge of the Sun's gravitational reach. Occasionally, passing stars or galactic tides disturb their orbits, sending them inward in dramatic arcs that sometimes bring them close enough to be seen from Earth. Each one we observe is a fleeting reminder of how vast our solar neighborhood truly is. Scientists believe that the Oort cloud may contain trillions of icy bodies, most no larger than mountains, but collectively forming an enormous reservoir of material left over from the earliest days of the solar system. These objects are so distant that none have ever been directly observed. Their existence is inferred from the behavior of comets and the gravitational limits of the Sun's reach. In a sense, the Oort cloud is the true frontier of the solar system, not a hard edge, but a fading boundary where the sun's influence gradually gives way to the pull of other stars. This realization fundamentally changes how we think about the solar system. It's not a small, neatly contained family of planets. It's a sprawling, layered structure that extends across light years of space. The planets we know, Mercury through Neptune, occupy only a tiny fraction of the Sun's realm. Beyond them lies an entire kingdom of ice and darkness, where time moves differently and sunlight is little more than a faint whisper. In fact, the spacecraft Voyager 1 and Voyager 2, launched in the late 1970s, are just beginning to touch the edge of this vast frontier. Both have crossed the heliopause, the boundary where the solar wind gives way to interstellar plasma, but even they haven't left the solar system entirely. They're still within the outermost reaches of the Oort cloud, and it will be tens of thousands of years before they drift beyond the Sun's gravitational influence altogether. So, the next time you see a diagram that ends the solar system at Pluto, remember this: our star's domain doesn't stop there. It extends into regions so distant that light from the Sun takes months to reach them. Beyond Pluto lies the Kuiper belt, the scattered disk, and then the Oort cloud, a cosmic frontier that blurs the line between our space and the galaxy beyond. The truth is that the solar system doesn't end. It fades. It dissolves gradually into the interstellar medium, like smoke blending into the night air. There's no wall, no edge, just a slow transition from the familiar to the unknown. And while that outer boundary is defined by distance, another illusion about the solar system lies much closer to home, one we see every single day with our own eyes. Because even the very color of the sun itself, the symbol of warmth and life, has been misunderstood for generations. If there's one image nearly every person shares when picturing the solar system, it's that of a bright yellow sun blazing at the center. Golden rays stretching across the void, bathing the planets in warm, honey-colored light. It's on flags, paintings, children's books, even the emoji we use every day. The yellow sun has become an icon of life, warmth, and energy. But here's the shocking truth: the sun isn't yellow at all. It's actually white. This might sound like a small detail, but it completely reshapes how we perceive the very heart of our solar system. When seen from space, outside of Earth's atmosphere, the sun shines as a pure, brilliant white star, not yellow or orange. Astronauts aboard the International Space Station describe sunlight as blindingly white, similar to the light from an arc welder or a camera flash. That's because the sun emits light across all visible wavelengths nearly evenly: red, orange, yellow, green, blue, indigo, and violet, blending together to form white light. So why do we see it as yellow from Earth? The answer lies in one of the most beautiful and subtle tricks of our atmosphere: Rayleigh scattering. As sunlight passes through Earth's air, the shorter wavelengths, blues and violets, are scattered in all directions by the tiny molecules of nitrogen and oxygen that make up our sky. The longer wavelengths, reds, oranges, and yellows, are scattered less and pass through more directly. This means that when we look up during the day, the sky itself appears blue because of the scattered short wavelengths, while the sunlight reaching our eyes directly seems slightly depleted of blue and violet light, leaving it with a warmer, golden tone. In other words, the sun looks yellow only because Earth's atmosphere is filtering and reshaping its true color. If you could stand on the moon, where there's no atmosphere to scatter the light, you'd see the sun as it truly is: a brilliant white orb suspended against the black backdrop of space. The same goes for Mars, where the thinner atmosphere scatters light differently, sometimes giving the sun a faintly bluish hue at sunset rather than yellow. This illusion isn't just about appearance. It also reflects a deeper misconception we've carried for centuries about our star. Even in the scientific age, the yellow sun became embedded in human imagination as a symbol of warmth and vitality. But in truth, the sun is a G-type main sequence star, or yellow dwarf, not because it looks yellow, but because of its temperature and spectral class. That scientific label, ironically, helped reinforce the myth. The sun's surface, or photosphere, glows at about 5,778 Kelvin, a temperature that produces light spanning the full visible spectrum. If you were to pass sunlight through a prism, as Isaac Newton famously did in the 17th century, you'd see all the colors spread out evenly in a rainbow. Combine those colors again, and you get white, the true color of our star. We can even prove this with physics. Astronomers measure the color of stars by analyzing their spectral distribution, how much light they emit at each wavelength. The sun's peak emission falls in the green portion of the spectrum, but since it emits similar amounts of red and blue light as well, the overall effect balances into white. The yellow we associate with sunlight is simply our atmosphere tinting that white balance toward the warmer end of the spectrum. It's worth noting, too, that the sun's color shifts throughout the day because of how much atmosphere its light passes through. When the sun is high in the sky, its light travels through less air, so it appears closer to white. Near sunrise or sunset, sunlight passes through much more of the atmosphere, scattering even more blue and green light, which is why the sun looks deep orange or red near the horizon. The fiery sunsets we admire aren't the sun changing color, they're the atmosphere painting over its true light. This illusion extends even beyond human vision. If we had evolved under different atmospheric conditions, or on another world entirely, our perception of sunlight would change. On Mars, the thinner carbon dioxide atmosphere scatters sunlight differently, making the sky pinkish and the sun pale. On Titan, Saturn's thick, hazy atmosphere would tint sunlight a deep orange. Each world in our solar system wears its own atmospheric lens, altering the color of the same white star shining on them all. The idea of a yellow sun isn't just an artistic simplification. It's a powerful symbol of how human perception shapes our understanding of reality. We see the universe not as it is, but as filtered through the narrow window of our senses and our environment. The sun's yellow glow is a perfect metaphor for this truth. Even something as constant and familiar as daylight is an illusion shaped by perspective. And yet, there's something poetic about that. The fact that our atmosphere turns the sun's white light into golden warmth makes life on Earth feel more vivid, more alive. The same process that scatters blue light into our sky also makes our sunsets red and our daylight golden. It gives our world its color, its beauty, and its sense of belonging under a nurturing star. The lie of the yellow sun isn't really deception. It's nature's artistry, a cosmic illusion painted by air and light. Still, once you know the truth, that our sun is a blazing white star streaking through the galaxy, the solar system starts to look very different. The serene golden model you learned about in school gives way to something far more dynamic, brilliant, and alive. And just as the sun isn't still, as we've already learned, it's not static in another way either, because the solar system it commands isn't perfectly balanced or eternally stable. Beneath its elegant clockwork appearance lies a restless system, always on the verge of subtle chaos. We've all been told that the solar system is a masterpiece of balance, a perfect cosmic clock, each planet moving with predictable precision in an eternal waltz around the sun. It's the image we grow up with: neat elliptical orbits, unchanging harmony, and a reassuring sense of stability. After all, the planets have been circling the sun for billions of years. Surely they'll keep doing so forever, right? But beneath that calm, elegant motion lies a far more turbulent truth. The solar system is not perfectly stable. It's a fragile dance balanced on the edge of chaos, a gravitational web so complex that even the tiniest nudge over enough time can send worlds tumbling into new paths, collisions, or exile into the cold dark beyond. The illusion of stability is just that. An illusion born of human timescales too short to witness the system's deeper restlessness. The first to hint at this hidden instability was Isaac Newton himself. His laws of motion and gravity could describe how planets move with astonishing accuracy. But when he tried to apply them to multiple bodies interacting with each other, something strange happened. Each planet's gravity tugged on every other planet, ever so slightly altering their orbits. Newton realized that these interactions meant the solar system wasn't a perfectly closed system at all. It was full of small, cumulative disturbances. He worried that given enough time, those gravitational tugs might add up, perhaps even tearing the system apart. Centuries later, mathematicians and physicists picked up where Newton left off, trying to solve what's known as the n-body problem, predicting the motion of multiple gravitationally interacting objects. It turns out that the equations describing even 3 bodies, say the Sun, Earth, and Jupiter, quickly become chaotic. The motions of such systems are deterministic, meaning they follow physical laws, but they're so sensitive to initial conditions that over long timescales, they become unpredictable. In other words, the solar system's apparent harmony hides the potential for chaos. Modern simulations using powerful supercomputers have confirmed this. When scientists model the orbits of the planets over billions of years, tiny differences in initial positions, even as small as a few millimeters, lead to radically different outcomes. Some simulations show Mercury's orbit destabilizing within the next 5 billion years, possibly sending it crashing into the Sun or even colliding with Venus. Others suggest that gravitational resonances, repeating orbital alignments between planets, could amplify over time, slightly altering the shapes and tilts of orbits across the entire system. These resonances are like cosmic feedback loops. When 2 planets periodically line up in their orbits, their gravitational pulls can reinforce each other, nudging their paths ever so slightly. Normally, these effects are small and self-correcting, but over millions or billions of years, those tiny nudges can add up, creating what's called chaotic diffusion, a slow, creeping drift toward instability. It's a bit like balancing a pencil on its tip. For a while, it may seem steady, but the tiniest disturbance eventually sends it toppling. And the chaos doesn't stop with the planets. The asteroid belt and the Kuiper belt are filled with objects constantly influenced by Jupiter, Saturn, and Neptune's gravitational fields. These influences can shift orbits, eject bodies into interplanetary space, or even send them spiraling inward toward Earth. Many of the comets we see are, in fact, the result of such slow gravitational nudges. Small perturbations magnified across eons, turning quiet ice rocks into brilliant, blazing wanderers. Even our Moon is subtly altering Earth's stability. Its gravitational pull gradually slows Earth's rotation and pushes the Moon a few centimeters farther away each year. These changes, imperceptible on human timescales, accumulate over geological epochs, reshaping tides, climate cycles, and even the length of our days. Then there's the ultimate wildcard, external forces. The solar system doesn't exist in isolation. It's constantly moving through the galaxy, influenced by the gravity of passing stars, molecular clouds, and dark matter clumps. A close stellar pass, something that happens every few million years, could tug at the distant Oort cloud, sending a rain of comets hurtling inward. In rare cases, a strong enough encounter could even slightly distort planetary orbits. Over billions of years, such encounters are inevitable, and they inject fresh unpredictability into an already delicate system. Despite all this, the solar system's chaos doesn't mean imminent disaster. Most simulations suggest that, for the next few 100 million years at least, things will remain relatively calm. But calm is a relative term. Over the course of billions of years, planetary orbits drift, inclinations change, and resonances build. Some models predict that in the far future, gravitational interactions could fling one of the outer planets, Uranus or Neptune, entirely out of the solar system. Others suggest that long-term chaos could lead to collisions between inner planets or cause the Sun's eventual expansion, as it becomes a red giant to swallow Mercury and Venus. So when we look at diagrams of the solar system, with their clean, elliptical lines and fixed spacing, we're really seeing a frozen snapshot of something far more alive and unpredictable. The solar system is like a great symphony, but one played on the edge of dissonance, stable enough to endure for billions of years, but always on the brink of subtle change. This reality humbles us. The harmony we take for granted, the steady rising of the sun, the dependable paths of the planets, is not eternal. It's temporary, a fleeting balance in the vast, shifting sea of cosmic gravity. The solar system isn't a clock. It's a dance, full of improvisation, where even the smallest misstep can echo across eternity. And if our sun's solitary grace and the planet's delicate balance are not as eternal as we thought, it makes one wonder, is our solar system even typical at all? Because, as it turns out, most star systems in the universe aren't solitary dances. They're partnerships, sometimes trios, sometimes more, locked in gravitational embraces that make our single star system an exception rather than the rule. When we look up at the night sky, it's easy to think that most of those tiny pinpricks of light, those countless stars scattered across the black, are just like our sun, solitary, shining alone, each with its own planetary family. After all, that's what we know. Our solar system orbits a single stable star, and for most of human history, we've assumed that's the cosmic norm. But here's one of the biggest revelations in modern astronomy. Our sun is the exception, not the rule. Most stars in our galaxy aren't solitary at all. They live in pairs, trios, or even larger families, bound together by gravity, orbiting around a shared center in intricate celestial dances that make our solar system look almost simple by comparison. In fact, studies show that over 50%, and possibly up to 70%, of all stars in the Milky Way are part of multi-star systems. Binary stars, or systems of two stars orbiting each other, are the most common, but triple and even quadruple star systems are far from rare. The lonely single-star setup we live in is a kind of cosmic minority. To understand why, it helps to go back to how stars are born. Stars emerge from giant molecular clouds, massive turbulent regions of gas and dust. As gravity pulls these clouds together, they collapse into smaller clumps, which eventually ignite into stars. But these collapses are rarely neat or isolated. The spinning motion of a collapsing cloud often causes it to fragment into multiple dense regions, each forming its own star. Those stars remain gravitationally linked, orbiting one another in delicate, eternal partnerships. These binary systems come in many varieties. Some have stars that orbit each other closely, so near that their outer atmospheres merge and exchange material. Others are widely separated, hundreds or even thousands of astronomical units apart, bound together only by the faintest gravitational pull. In some cases, one star is much more massive and luminous, dominating the system, while its companion is a faint red dwarf or even a white dwarf, the burnt-out remnant of a star that has already lived and died. One of the most famous examples is Alpha Centauri, our nearest stellar neighbor, located just over 4 light-years away. It's not one star, but 3. The two main stars, Alpha Centauri A and Alpha Centauri B, orbit each other relatively closely, while a third, Proxima Centauri, circles them from much farther out. Proxima is a faint red dwarf, invisible to the naked eye, but it's currently the closest star to Earth. It even hosts at least one known planet, Proxima b, located in its habitable zone. Imagine that, a planet orbiting one member of a triple star system, its skies illuminated not by one sun, but by 3. Triple star systems like Alpha Centauri are mesmerizing to imagine. On a world orbiting one of the inner stars, the sky would never be truly dark. Multiple suns would rise and set, casting overlapping shadows, creating ever-changing patterns of light. Days could be longer or shorter depending on orbital alignments. Sunsets might come in pairs, each one painting the horizon in a different color. For all our technological advances, even our best science fiction often struggles to capture the sheer surreal beauty of what such a sky might look like. Even within binary systems, the complexity is astonishing. Some binaries are eclipsing binaries, where one star periodically passes in front of the other, dimming the system's light as seen from Earth. These eclipses allow astronomers to study stellar masses and compositions in ways we can't with single stars. Others are spectroscopic binaries, where the stars are so close together that we can't distinguish them visually, but we can detect their orbital motion through the Doppler shifts in their light. And the diversity doesn't stop there. Some multi-star systems include neutron stars or black holes orbiting normal stars, forming some of the most extreme environments in the universe. In others, one star might siphon gas from its companion, creating explosive outbursts known as novae. These interactions can even end with one star tearing its partner apart, feeding on its remains like a cosmic predator. The universe, it seems, is full of stellar relationships, sometimes harmonious, sometimes violent, always fascinating. So why are we alone? Why is our sun a solitary wanderer? That question remains one of the quiet mysteries of astronomy. It's possible that our sun once had a twin, a binary companion that drifted away long ago. Some scientists speculate that such a companion, nicknamed Nemesis, might have orbited far from the Sun, occasionally disturbing the Oort cloud and triggering comet showers that impacted Earth. There's no evidence of Nemesis today, but the theory remains intriguing, hinting that our Sun's solitude might be an accident of cosmic history rather than a natural design. Being a single star may actually be one of the reasons life could thrive here. Binary and multi-star systems often have unstable gravitational environments where planets are tugged between competing stellar forces. In many such systems, planetary orbits can become distorted, elongated, or even ejected entirely. In others, intense radiation from close stellar companions might strip planets of their atmospheres or boil away their oceans. Our Sun's quiet isolation provides stability, a calm gravitational haven where life had time to evolve undisturbed for billions of years. Still, there's something humbling about knowing that our solar system, so familiar and orderly, is the exception in a galaxy filled with complex star families. It reminds us that our view of normal is shaped by our limited perspective. We orbit a single white star, unaware that most other worlds orbit in pairs or trios, bathed in shifting lights and shadows. And when you think about it, that realization ties back to almost every lie we've uncovered so far. The idea that what we see, or think we know, is universal, when in truth, it's just one small variation among countless cosmic possibilities. Even the asteroid belt, that famous gap between Mars and Jupiter we imagine as a crowded field of drifting rocks, is another place where the truth is very different from the myth, not dense and perilous, but vast and lonely. When most people imagine the asteroid belt, Their minds immediately conjure scenes straight out of science fiction. Jagged rocks tumbling through space, asteroids colliding and scraping past one another, and brave starships weaving through a chaotic maze of spinning debris. Hollywood has done an excellent job of making the asteroid belt seem like a cosmic minefield, dense, dangerous, and endlessly dramatic. But the reality is far less cinematic, and in some ways, far more awe-inspiring. The asteroid belt, located between the orbits of Mars and Jupiter, isn't a tightly packed field of rocks at all. It's a vast, mostly empty region of space, scattered with a few small bodies separated by enormous distances. The truth is, if you were floating within the asteroid belt, you'd probably see nothing. Not a single rock, not a single object in sight. It would feel like open space. Let's start with the scale. The asteroid belt stretches from roughly 2.1 to 3.3 astronomical units, AU, from the Sun. That's between 300 and 500 million kilometers from our star. It's an enormous region, wide enough to fit several entire planetary orbits within it. Yet the total mass of all the asteroids combined is surprisingly small, less than 5% of the Moon's mass. If you gathered up every asteroid, rock, and pebble in the belt and molded them into a single body, you'd end up with something smaller than Earth's moon. And while there are millions of asteroids, they are astonishingly far apart. The average distance between two asteroids in the main belt is about 600,000 miles, nearly 1 million kilometers. To put that in perspective, if each asteroid were the size of a car, the next one would be hundreds of miles away, far beyond the horizon. Spacecraft like NASA's Dawn and New Horizons have traveled through the asteroid belt multiple times without ever coming close to hitting anything. The chances of a random collision are astronomically small. So how did this giant, mostly empty expanse come to be? The answer lies in Jupiter's powerful gravity. Billions of years ago, during the formation of the solar system, this region was filled with dust, rock, and ice, the raw ingredients for a planet. But as those fragments tried to clump together, Jupiter's immense gravitational pull continually disrupted them. Its tugs stirred the region like a spoon in soup, preventing the material from coalescing into a single large body. The result? A region of leftovers, a failed planet that never quite formed. Even today, Jupiter continues to shape the belt. Its gravity establishes orbital resonances, zones where its pull regularly disrupts asteroid paths. These resonances create gaps in the belt, known as Kirkwood gaps, where few asteroids can survive for long. Over millions of years, these gaps have sculpted the belt into a series of bands and clusters, making it more structured than it appears in popular depictions. The asteroids themselves are incredibly diverse. Some are dark and carbon-rich, known as C-type asteroids, remnants of the early solar system's original material. Others, called S-type, are brighter and rockier, containing silicates and metals. And then there are M-type asteroids, metallic fragments that may be the exposed cores of ancient, shattered protoplanets. The largest of them, Ceres, is about 940 kilometers across, so big that it's actually classified as a dwarf planet. Others, like Vesta and Pallas, are smaller but still large enough to be nearly spherical due to their own gravity. Between these giants, the smaller asteroids, from mountain-sized rocks down to pebble-sized fragments, drift quietly through space, each following its own orbit around the Sun. They move fast, often tens of thousands of kilometers per hour, but because of the sheer scale of the belt, they rarely come close to one another. In fact, when two asteroids do collide, it's such a rare event that astronomers can study the debris field for centuries. So why do so many people believe the asteroid belt is densely packed? The answer is simple. Our brains struggle to grasp the true scale of space. When we see maps of the solar system, everything is compressed. The planets are drawn far too close together, and the asteroids are shown as tightly clustered swarms just to make them visible. In truth, space is so vast that even the most crowded regions, like the asteroid belt or the Kuiper belt, are mostly emptiness. It's almost poetic, really. The belt that Hollywood portrays as dangerous and violent is, in reality, one of the quietest, loneliest regions of our solar system. You could fly for weeks or months through it and never see another object. But that emptiness carries a kind of beauty, a stark reminder that even in the quiet spaces between planets, the remnants of creation linger, scattered and patient, telling the story of a planet that never was. And yet, despite its emptiness, the asteroid belt has had a profound effect on Earth's history. Some of the asteroids occasionally stray from their stable paths, pulled by Jupiter or nudged by collisions, and wander inward toward the Sun, sometimes crossing Earth's orbit. These near-Earth asteroids have struck our planet many times over its history, shaping evolution, resetting ecosystems, and even triggering mass extinctions. The very event that wiped out the dinosaurs likely began in this quiet, forgotten region between Mars and Jupiter. So while the asteroid belt might not be the chaotic labyrinth we once imagined, its influence is anything but minor. It's a place of silence and vastness, but also of potential, danger, and deep history. It's where the ancient debris of creation still floats, quietly waiting for its next chapter in the solar system's story. And as we move past the belt, outward toward the inner planets, another myth waits for us. One that's been repeated so often it's become almost cliché, that Venus is Earth's twin, our planetary sister, a near-perfect reflection of our world. But that twin turns out to be one of the most hostile, alien places imaginable, a world that shows how deceptive appearances can be. Venus has long been called Earth's twin, and at first glance, it's easy to see why. It's nearly the same size, almost the same mass, and made of similar rocky materials. It orbits close to our planet, and for centuries, it even seemed like a mirror world. The same glowing sibling shining brightly in the twilight sky, called the morning star, or evening star. For generations, astronomers dreamed of Venus as a lush, tropical planet hidden beneath thick clouds, perhaps covered in jungles, oceans, and strange alien life. But the truth could not be more different. Beneath those pearly clouds, Venus is not a paradise. It's a nightmare, one of the most hostile environments in the entire solar system. Instead of Earth's gentle blue skies, Venus is wrapped in a choking atmosphere of carbon dioxide, with clouds of sulfuric acid swirling above. The pressure at its surface is about 92 times that of Earth's, equivalent to being nearly a kilometer underwater. If you somehow stood on Venus, the air itself would crush you in seconds. And then there's the heat, an unimaginable, searing, relentless heat. Venus's average surface temperature is about 465 degrees Celsius, 869 degrees Fahrenheit, hot enough to melt lead, zinc, or tin. In fact, Venus is hotter than Mercury, even though it's farther from the Sun. That's because Venus has fallen victim to a runaway greenhouse effect. Its thick carbon dioxide atmosphere traps heat so efficiently that almost none escapes into space. The Sun's energy enters through the clouds, bounces off the surface, and becomes trapped again and again until the entire planet glows with deadly warmth. If Earth is a carefully balanced climate machine, Venus is what happens when that balance collapses completely. Billions of years ago, Venus may have had oceans and milder temperatures. Some models suggest it once could have been habitable, perhaps even home to liquid water. But as the young sun grew brighter, more water evaporated, and water vapor, a powerful greenhouse gas, trapped even more heat. The oceans boiled away, the surface baked dry, and carbon dioxide, released from the rocks and the dying oceans, took over. The result was an unstoppable feedback loop. More heat led to more gas, which led to even more heat. Eventually, Venus transformed from Earth's twin into its warning. The atmosphere that remains is not only dense and hot, but also deadly in composition. It's made of roughly 96% carbon dioxide, with only a trace of nitrogen and almost no oxygen. The upper layers are filled with droplets of sulfuric acid that reflect sunlight, giving Venus its bright appearance from afar. But beneath those clouds, sunlight barely penetrates. The surface lies in a perpetual orange haze, dimly lit and eternally scorching. The winds on Venus are another paradox. High above the surface, in the upper atmosphere, hurricane-force gales roar around the planet at 360 kilometers per hour, 220 miles per hour, whipping the clouds into a global vortex. But on the surface itself, where the air is so thick it feels like a liquid, the wind barely stirs. Only a few kilometers per hour, yet strong enough to slowly move dust and sculpt rocks over eons. And then there's the rain. Not water, but acid. In the upper clouds, sulfuric acid condenses and falls, only to evaporate before it reaches the ground, creating a bizarre cycle of toxic rain that never truly lands. Perhaps the most haunting detail about Venus is how eerily quiet it is. There's no sound of wind howling, no flowing water, no weather as we know it, just stillness and heat. The Soviet Venera landers, the only spacecraft ever to survive on its surface, and only for a few minutes each, recorded a world of broken, desolate plains, dotted with volcanic rocks and smothered by a yellow haze. The temperature melted their electronics, the pressure crushed their hulls, and the acid corroded their instruments almost instantly. Venus is also one of the most volcanically active places in the solar system. Radar mapping by NASA's Magellan spacecraft revealed vast lava plains, mountains taller than Everest, and possible signs of active volcanoes that may still erupt today. Some scientists even suspect that Venus periodically resurfaces itself, that volcanic eruptions are so massive and widespread, they bury the planet's crust beneath fresh lava every few 100 million years. It's a world in constant geologic upheaval, hidden beneath an unyielding sky. But for all its horrors, Venus is invaluable to science. It shows us what can happen when a planet's climate spirals out of control. A cautionary tale written in molten rock and acid clouds. Studying Venus helps scientists understand not only the extremes of atmospheric physics, but also the delicate balance that keeps Earth habitable. In a sense, Venus is both our twin and our mirror, reflecting not what we are, but what we could become if we fail to protect our own fragile environment. There's a tragic poetry in it. Venus, once seen as Earth's sister, is now its ghost. A world that may have started like ours, but took a different path, one that ended in fire. When we gaze at it in the evening sky, glowing softly beside the moon, we're not seeing a twin. We're seeing a warning, a reminder that beauty can hide catastrophe. And just as Venus's true nature turned out to be far more complex than its glowing appearance, the same goes for its red-hued neighbor, Mars. We call it the red planet, but even that title hides a deeper truth. Mars isn't simply red, it's a world of many colors, moods, and mysteries waiting to be uncovered. When people think of Mars, one image dominates: a small, dry, dusty, red planet hanging in the blackness of space. It's been called the Red Planet for centuries, a name so ingrained that it's become part of its identity in culture, myth, and science. From the fiery god of war to the rusty landscapes in countless movies, Mars has always been painted as a world cloaked entirely in red dust. But like so many of the solar system's myths, that simple image hides a much richer and more complex truth. Mars isn't just red, it's a planet of colors, textures, and tones that change with the light, the atmosphere, and even the seasons. The signature red hue of Mars does have a real basis in science. Its surface is covered with a fine layer of iron oxide, essentially rust, that gives the soil its reddish tint. Billions of years ago, Mars had abundant water, and that water reacted with iron-rich minerals in the rocks and dust, oxidizing them just like iron rusts on Earth. Over eons, winds ground that rusted rock into powder, spreading it across the surface. The result? A planet wrapped in a thin coating of reddish dust, reflecting sunlight in warm, rusty tones. But here's the fascinating part: that red dust is only skin deep. The rocks beneath vary wildly in color, from deep browns and blacks to golden tans, grays, and even blues and greens. When spacecraft like NASA's Curiosity and Perseverance rovers brush away the top layer of dust, they reveal a palette that would surprise anyone who thinks of Mars as monochrome. Some exposed rocks have basaltic origins, making them dark grey or even bluish. Others are rich in sulfates or clays that give them lighter, more earthy hues. In fact, some parts of Mars, like the hematite ridge in Gale Crater, shimmer in subtle purples and silvers under the right lighting. Even Mars's skies, so often imagined as a dull red haze, tell a different story. During the day, the Martian sky tends to appear a buttery pink or apricot color, not deep red. That's because the fine dust in the atmosphere scatters sunlight differently than Earth's air does. On our planet, shorter blue wavelengths scatter the most, giving us blue skies. But on Mars, the much larger dust particles scatter longer wavelengths, meaning more of the red and orange light stays visible while the blue light gets absorbed and refracted. The result is a pale salmon-colored sky stretching above a coppery horizon, a haunting, alien glow unlike anything on Earth. Then there are the sunsets. If you were standing on Mars at dusk, you wouldn't see a fiery red sunset like on Earth. You'd see the exact opposite, a blue one. As the sun dips below the horizon, the light passes through a thicker layer of the Martian atmosphere, which filters out the red wavelengths instead, allowing the blue light to dominate near the sun. The result is a delicate blue halo, fading into orange-pink skies, one of the most surreal and beautiful sights in the solar system. Mars's sunsets are so striking that NASA's rovers have captured them in stunning detail, showing a sky where day and night blur into soft, metallic twilight. And those famous Martian dust storms? They're not purely red either. Depending on the mineral makeup of the dust and how sunlight scatters through the thin air, they can appear golden, orange, or even a murky brown-grey. Some storms are so vast they can blanket the entire planet for weeks, dimming the sunlight to a faint glow. In those moments, the entire world takes on a muted, ghostly hue, more like a sepia photograph than a red desert. From orbit, the color complexity becomes even more vivid. High-resolution images from spacecraft like Mars Reconnaissance Orbiter show landscapes painted in multicolored strokes, oxidized reds, volcanic blacks, frost-tipped whites, and even pale blues from ice-rich soils. The polar caps, composed of water ice and frozen carbon dioxide, gleam bright white against the dusty terrain, while ancient riverbeds snake across the planet like dark, branching veins, relics of a wetter past. Even the way Mars changes color over time is fascinating. Seasonal winds whip up dust storms that move and settle across the surface, subtly altering the planet's appearance from orbit. Some areas darken as dust is swept away, revealing basaltic rock beneath. Others brighten as fine dust settles anew. Mars, in other words, isn't just red. It's alive with color, its surface always shifting, always changing in tone and contrast. So why do we cling to the image of a red planet? Partly because of simplicity, and partly because that first impression from early telescopic observations stuck. When 19th century astronomers like Giovanni Schiaparelli and Percival Lowell looked at Mars through primitive optics, they saw reddish hues dominating the disk. With no way to distinguish subtle color variations, they recorded it as the Red Planet, and the name endured. The mythology of Mars as a world of fire and blood grew from that image, reinforced by its association with the Roman god of war. But the more we've learned about Mars, the more it has defied that old narrative. The red is still there, yes, but it's layered with greys, golds, blues, and whites. A living canvas painted by geology, wind, and time. To call it simply red is to erase its beauty, its nuance, and its history. And in that way, Mars mirrors much of what we've learned about the solar system as a whole. The more we look, the more we realize that the truth is always richer and stranger than the myth. Mars's color changes with the light, just as our understanding of the cosmos changes with knowledge. The closer we get, the more the picture evolves. And speaking of what we don't yet know, that brings us to one of the biggest misconceptions of all, the idea that we've already charted the solar system, that we know its planets and moons in detail. The reality is humbling. Even after centuries of exploration, there are worlds in our own backyard that remain almost completely mysterious. We like to think we've conquered the solar system, that we've mapped it, photographed it, and understood it. After all, we've walked on the moon, landed rovers on Mars, flown probes to the outer planets, and captured high-resolution images of worlds billions of kilometers away. When you look at the incredible photos from NASA or ESA, Saturn's rings, Jupiter's storms, Pluto's icy heart, it's easy to believe we know our solar system inside and out. But the truth is far less comforting. We've barely scratched the surface. For all our achievements, humanity has physically visited, with robotic probes, only a handful of the solar system's worlds. Most of what we know comes from fleeting flybys, partial scans, or distant telescopic observations. Even today, entire planets and dozens of moons remain largely unexplored, their mysteries hidden behind veils of distance, darkness, and time. The idea that we know the solar system is one of the most persistent and misleading myths of modern astronomy. Let's start with the outer planets, Uranus and Neptune. These two distant ice giants sit at the edge of our understanding, orbiting the Sun more than 2.5 billion kilometers away. And yet, the sum total of direct human observation of both worlds comes from a single spacecraft, Voyager 2. It flew past Uranus in 1986 and Neptune in 1989 for just a few hours each, snapping a limited series of images before continuing on toward interstellar space. That's it. We haven't returned since. Think about that. In the entire history of space exploration, we've visited Uranus and Neptune only once, and briefly. Everything we know about their weather systems, magnetic fields, and moons comes from data collected in the 1980s, using technology that's now considered ancient. Imagine trying to understand Earth by looking out the window of an airplane for a few minutes while flying by. That's essentially our level of knowledge about those planets. And what little Voyager 2 revealed only deepened the mystery. Uranus is a strange, ghostly blue-green world that rotates on its side, tilted more than 90 degrees. A planet literally rolling through space. Its magnetic field is bizarre, lopsided, and offset far from its center, defying our models of planetary magnetism. Its atmosphere is calm compared to Jupiter or Saturn, yet it may hide a deep, boiling ocean of water and ammonia beneath its clouds. An exotic, icy layer that could generate powerful internal heat. But we don't know for sure. The data are too sparse. Neptune, by contrast, is wild, a world of violent winds and turbulent weather. Voyager captured the famous image of the Great Dark Spot, a massive storm system larger than Earth, swirling in the upper atmosphere. But by the time the Hubble Space Telescope looked decades later, the storm was gone, replaced by others. Neptune's winds are the fastest in the solar system, reaching speeds of 2,100 kilometers per hour, 1,300 miles per hour. Yet we still don't fully understand what drives them. Is it heat escaping from the core? Some unknown dynamic of its icy atmosphere? We simply don't know. And then there are their moons, mysterious worlds orbiting in cold shadow, many of which have barely been photographed. Uranus has at least 27 known moons, most of them named after Shakespearean characters: Titania, Oberon, Ariel, Miranda, and others. Voyager's brief encounter revealed surfaces scarred by fractures, cliffs, and canyons that suggest geological activity. Miranda, for instance, looks like a jigsaw puzzle, a patchwork of terrains as if the moon was shattered and reassembled. What could cause such chaos? Internal heating? Ancient impacts? We don't have enough data to say. Neptune's largest moon, Triton, is even more enigmatic and may hold some of the most tantalizing clues about life in the outer solar system. Unlike most moons, Triton orbits backward, a retrograde path that suggests it wasn't born with Neptune but was captured long ago, possibly from the Kuiper Belt. It's one of the coldest places in the solar system, with surface temperatures around -235 degrees Celsius, -391 degrees Fahrenheit. Yet when Voyager flew past, it spotted something astonishing: active geysers spewing nitrogen gas into space. That means Triton isn't a dead rock. It's alive with internal energy. Beneath its frozen crust may lie a subsurface ocean, potentially one of many in the outer solar system that could harbor the chemical ingredients for life. And yet, no spacecraft has returned to confirm it. Beyond Neptune, our ignorance only grows. The Kuiper Belt and Oort cloud, populated by trillions of icy bodies, remain almost completely uncharted. New Horizons gave us a breathtaking view of Pluto in 2015, a small world with mountains of water ice, flowing nitrogen glaciers, and a heart-shaped plain that melted human hearts as much as it stunned scientists. But since then, the probe has only flown by one more object, Arrokoth, and the rest of that frozen realm remains invisible to us, except as faint points of light. Even among the planets we think we know well, there are vast gaps in our understanding. Take Mercury, for instance, the closest planet to the Sun. Only 2 spacecraft have ever visited it: Mariner 10 in the 1970s and Messenger in the 2010s. We've only recently begun to understand its bizarre, iron-rich core and its unexpected traces of water ice hiding in craters that never see sunlight. Or Venus, which we've discussed, a planet we can't even observe directly from the surface for more than an hour without our probes dying. And then there are the moons, the true hidden worlds of the solar system. Jupiter's moons alone are a miniature solar system in themselves. Europa, with its icy crust and ocean beneath, could hide alien life. Io is a volcanic hellscape, its surface constantly reshaped by eruptions. Ganymede is the largest moon in the solar system, larger than Mercury, and has its own magnetic field. Callisto, pocked with ancient craters, may conceal another subsurface ocean beneath its dark crust. Saturn's moons tell equally strange tales. Titan, with lakes of liquid methane and a dense orange atmosphere. Enceladus, with geysers of water vapor shooting into space from an ocean below. And yet, despite all these wonders, we've explored only a fraction of them. We've never landed on any moon beyond Titan. We've never drilled into Europa's ice. We've never sent an orbiter to Neptune or Uranus to study their hidden weather and mysterious magnetism. We have names for hundreds of moons, but for most of them, we know little more than their shape and orbit. It's humbling to realize that in 2025, nearly 70 years after we first ventured into space, there are entire worlds, potentially habitable ones, that remain untouched, unseen, and almost entirely unknown. We've spent more time studying exoplanets dozens of light years away than we have the moons orbiting our own neighboring giants. The "we know the planets" lie isn't malicious. It's the result of human optimism. We love to think of the solar system as charted territory, a place we've mapped and mastered. But the truth is, we're still at the beginning. We've mapped the continents, but not the oceans. And the outer solar system is a vast, dark ocean we've barely dipped our toes into. And if the planets and moons we've visited hold so many surprises, imagine what the early days of the solar system must have been like, when these worlds were being born, moved, and remade in the violent crucible of cosmic creation. Because the story of how our solar system formed isn't the neat, organized tale we learned in school. It's a chaotic, explosive saga of collisions, migrations, and reshuffling. A story that rewrote itself again and again before settling into the delicate balance we know today. We were taught that the solar system's birth was simple, even elegant. That it began as a smooth, swirling disk of gas and dust, gently spinning around the young sun. Over millions of years, this disk supposedly organized itself into perfect order, dust grains sticking together, growing into pebbles, then rocks, then planets. A cosmic ballet, unfolding in harmony. Every world forming where it belonged, each orbit neatly spaced. It's a comforting image, predictable, serene, and inevitable. But the truth, as modern science has uncovered, is far messier and far more dramatic. The formation of our solar system was not a calm ballet. It was a chaotic war zone. Planets didn't glide gracefully into existence. They collided, migrated, and reshuffled in a violent cosmic struggle that left scars still visible today. The neat textbook version of how we came to be is more like a storybook myth than a reflection of reality. Around 4.6 billion years ago, our sun was born from a collapsing cloud of gas and dust, likely triggered by the shockwave of a nearby supernova. As it ignited into a star, the remaining material flattened into a rotating disk. That part is true. But within that disk, chaos reigned. Dust particles clumped together through electrostatic attraction. But as they grew larger, collisions became increasingly destructive. For every grain that stuck, countless others shattered. The process was more of a cosmic demolition derby than a peaceful assembly line. Eventually, the survivors grew large enough for gravity to take over, pulling in surrounding material and forming planetesimals, the building blocks of planets. But these young worlds didn't quietly stay in place. They smashed into one another in titanic impacts that released unimaginable energy. One of those collisions, scientists now believe, created our moon, when a Mars-sized body, dubbed Theia, slammed into the early Earth about 4.5 billion years ago. The impact was so violent it vaporized part of both worlds, sending molten debris into orbit that eventually coalesced into the moon. And Earth wasn't alone in suffering such cataclysms. Mercury, small and dense, likely lost much of its outer mantle in a similar impact. Venus may have been knocked onto its strange backward rotation by a massive collision. Uranus's extreme 98-degree tilt, essentially rolling around the Sun on its side, almost certainly came from another colossal smash-up. These are not the marks of a neatly formed system. They're the scars of creation by chaos. But the most revolutionary discoveries of the last few decades have revealed that the planets didn't even stay where they formed. They moved, dramatically. According to what astronomers now call the Nice model, named after the city in France where it was developed, the giant planets, Jupiter, Saturn, Uranus, and Neptune, once occupied very different orbits, far more compact than today. Over time, gravitational interactions between them and the remaining debris caused them to migrate outward, reshuffling the structure of the entire solar system. At one point, Jupiter and Saturn may have fallen into a gravitational resonance, their orbits sinking in such a way that their combined gravity destabilized the outer disk of icy bodies. This triggered a period of cosmic chaos known as the Late Heavy Bombardment, during which a storm of asteroids and comets bombarded the inner planets, carving out the ancient craters we still see on the Moon and Mercury. Some scientists even think this event delivered crucial ingredients, water and organic molecules, to Earth, helping set the stage for life. Neptune, too, didn't form where it is now. Evidence suggests it was born closer to the Sun and later migrated outward, flinging smaller bodies into distant, eccentric orbits and creating the Kuiper Belt in the process. Some of those ejected objects may have become part of the distant Oort cloud, while others were hurled completely out of the solar system, wandering forever through interstellar space. Even the asteroid belt, that quiet graveyard between Mars and Jupiter, is a monument to this ancient chaos. It's thought that the region once contained far more material, possibly enough to form a planet. But Jupiter's gravity continually stirred it up, preventing it from coalescing. The asteroids we see today are the survivors of that violent gravitational tug-of-war, the remnants of a failed world. And that's just the early solar system. The story didn't end when the planets settled into their current orbits. Even now, subtle gravitational resonances and chaotic dynamics continue to shape their paths. Some scientists suspect that there might once have been a fifth giant planet, an ice giant that was flung out of the solar system entirely during those early upheavals. Others point to lingering evidence of another massive, unseen object far beyond Neptune, the hypothetical planet 9, whose gravity could explain the strange clustering of certain distant icy bodies. If such a planet exists, it would be a ghost from that primordial era, silently circling the Sun hundreds of times farther away than Neptune. This new understanding has completely overturned the tidy narrative we once believed. The solar system didn't form like clockwork. It evolved through chaos, through collisions, migrations, and endless change. Every planet's orbit, every moon's tilt, every crater on every surface is a fossil of that violent past. Earth's own habitability, the position of its orbit, the balance of its climate, may be a fragile accident born of those ancient cosmic collisions. What makes this revelation so profound is how it mirrors the broader truth of nature. Creation is rarely orderly. From galaxies to stars to planets to life itself, the universe builds through trial and error, destruction and rebirth. The solar system's beauty, its symmetry and balance, is not the result of perfect design, but of countless chaotic events that somehow, miraculously, found equilibrium. And even the chaos of planetary formation isn't the end of the story. Beyond the planets, another kind of object drifts through the solar system, not massive enough to be worlds, not quite alive, but vital to our very existence. For centuries, we called them dirty snowballs, simple relics from the dawn of time. But just like everything else in this vast cosmic neighborhood, comets have proven to be far more complex and far more important than the old myths ever suggested. Comets have always carried an air of mystery. For most of human history, they were seen as omens, harbingers of disaster, divine messengers, or warnings from the heavens. When one suddenly appeared in the night sky, blazing a tail across the stars, entire civilizations trembled. But as science advanced, our view of comets shifted from superstition to science, from fear to fascination. And for decades, one simple phrase dominated textbooks and documentaries alike. Comets are dirty snowballs. It was the astronomer Fred Whipple in the 1950s who coined that phrase. He proposed that comets were lumps of frozen gases mixed with dust and rock, dirty snowballs orbiting the Sun from the distant edges of the solar system. As they approached the Sun, the heat would vaporize their icy surfaces, creating the glowing comas and long, beautiful tails that we see from Earth. It was a compelling and elegant model, and for a long time, it fit the data. Comets seemed like time capsules from the birth of the solar system, simple relics made of ice and dust, untouched for billions of years. But as our technology improved, as spacecraft actually visited these enigmatic wanderers, that simple picture shattered. The more we looked, the more we realized that comets are not just dirty snowballs. They are far more complex, far more diverse, and far more vital to understanding both the history of the solar system and the origins of life itself. The first real glimpse beneath a comet's veil came in 1986, when ESA's Giotto spacecraft flew past Halley's Comet. What it found was shocking. Instead of a fluffy snowball, Halley's nucleus was dark, jet black, reflecting less sunlight than coal. It wasn't covered in glistening ice, as scientists had expected, but rather coated in a thick, carbon-rich crust. Jets of gas and dust burst violently through fissures in this crust as the sun's heat reached deeper layers, producing the glowing coma. The snowball idea could no longer explain what we were seeing. Subsequent missions deepened the mystery. When NASA's Deep Impact Probe deliberately slammed into Comet Tempel 1 in 2005, the explosion revealed that much of the comet's interior was made of dust, complex organic molecules, and surprisingly little ice. And then came the Rosetta mission, one of the most ambitious projects in space exploration history. In 2014, after a decade-long journey, the European Space Agency's Rosetta spacecraft finally rendezvoused with Comet 67P/Churyumov-Gerasimenko, sending down a small lander named Philae to touch its surface. What Rosetta and Philae discovered changed our understanding of comets forever. First, 67P's surface wasn't smooth or icy. It was rugged, rocky, and strangely shaped, more like a mountain than a snowball. The lander's instruments found the ground to be so hard that its harpoons couldn't anchor. The comet's crust was dense, covered with organic compounds, complex molecules containing carbon, hydrogen, oxygen, and nitrogen, the very building blocks of life. Then came the real surprise. Rosetta's instruments detected amino acids, including glycine, one of the essential components of proteins. They also found phosphorus, another element crucial to DNA and cell membranes. These weren't random chemical curiosities. These were biologically relevant molecules, formed naturally in the cold depths of space and preserved for billions of years. That discovery carried profound implications. It suggested that comets may have played a crucial role in seeding early Earth with the ingredients of life. During the chaotic early years of the solar system, when impacts were common, countless comets and asteroids bombarded our planet. Earth, then newly formed and molten, was cooling, but it had likely lost much of its original volatile materials, including water and organic compounds. The impacts from comets could have replenished those essentials. Indeed, isotopic studies of cometary material suggest that at least some of Earth's water, and possibly the precursors of life's chemistry, came from these frozen travelers. In this sense, comets are not just relics of creation. They're delivery systems of life, cosmic couriers carrying water and organic molecules across billions of kilometers of space, scattering the seeds of biology wherever they land. And the evidence continues to grow. Organic molecules found in comets are astonishingly complex. Some are polycyclic aromatic hydrocarbons, PAHs, large, ring-like molecules that form in interstellar space and can lead to more complex biochemistry. Others are simple sugars, alcohols, and acids, the kinds of molecules that, under the right conditions, can assemble into the precursors of RNA and DNA. It's as if the solar system itself came with a built-in chemistry set, scattering the tools of life across its early surfaces. But comets don't just carry life's building blocks, they carry history. Because they spend most of their lives in deep freeze, far from the sun, they preserve the original material from which the solar system formed. Studying them is like opening a time capsule from 4.6 billion years ago. The gases trapped inside, the dust embedded within, the isotopic ratios, all of it provides clues about the conditions that existed before planets even existed. We've also learned that comets are not all the same. Some are long-period comets, coming from the distant Oort cloud and taking thousands or even millions of years to complete one orbit. Others are short-period comets, originating from the Kuiper belt, circling the Sun every few decades. These two populations likely formed in different regions of the early solar system, shaped by the gravitational migrations of Jupiter and the other gas giants. Each carries a different chemical fingerprint, different clues to the processes that built our cosmic neighborhood. And yet, despite all we've learned, comets still defy simple explanations. Their surfaces are strange, their behavior unpredictable. Some disintegrate suddenly as they approach the Sun. Others, like Comet 29P/Schwarzmann-Wachmann, erupt repeatedly without warning, spewing gas and dust like a volcano in space. We've even observed comets that blur the line between asteroid and comet, bodies that seem to switch personalities, dormant for centuries, then suddenly flaring back to life when heated. What this tells us is that comets are not just icy leftovers. They're active, evolving participants in the solar system. They've been sculpted by sunlight, gravity, and time, reshaped and reawakened over and over across billions of years. Each comet that streaks across our sky is both ancient and alive, carrying within it the story of the solar system's birth, and possibly the origins of life itself. When you realize that, the old phrase, "dirty snowball," feels almost insulting. A comet isn't dirty, and it isn't simple. It's a cosmic library, holding volumes written in the language of chemistry and physics, a record of how chaos became structure, and how lifeless matter might have crossed the threshold into life. And yet, as fascinating as comets are, they've also fueled one of humanity's oldest confusions: the blurred line between astronomy and astrology, between science and superstition. Because for millennia, people didn't just see comets as natural phenomena. They saw them as omens that shaped human fate. And even today, that confusion between planetary motion and human destiny lingers, a myth that refuses to die. The real mystery of our solar system isn't any single myth or misconception, not the flat orbits, not the circular paths, not even Pluto's demotion or the Sun's true color. The greatest lie ever told about our solar system is that we already understand it, that we've mapped it, mastered it, reduced it to diagrams, and locked its truths into tidy categories, that the solar system is a finished story, one we've already read cover to cover. But it isn't. It never was. The solar system is still writing itself, and every time we think we've reached the last chapter, something new emerges that forces us to rewrite the beginning. We've spent centuries building our understanding of the cosmos layer by layer, from Galileo's first glimpse of Jupiter's moons through a crude telescope, to the intricate simulations and spacecraft data we now use to probe the edges of interstellar space. Each discovery seemed to bring us closer to a complete picture. But if you step back and really look, what you see isn't completion. It's constant transformation. Every fact we once held sacred has eventually been overturned. Once, we believed the Earth was the center of the universe. Then we believed the sun was the center of everything. Then we learned the sun itself was just one star among hundreds of billions, orbiting a galaxy that's just one among trillions. Each revelation pushed us outward and downward, showing that we are neither the center nor the conclusion of creation, but a small part of an infinite unfolding mystery. And the solar system, our own immediate cosmic home, has mirrored that process perfectly. For centuries, we saw it as a simple clockwork machine. The planets moved in predictable paths, orbiting obediently, forever unchanged. But the deeper we've looked, the more we've found that nothing about it is simple. It's not flat, it's not circular, it's not stable, it's not even isolated. It's a dynamic, chaotic, interconnected ecosystem, alive with energy, motion, and uncertainty. It evolves, reshapes itself, and resists final definitions. The sun, that constant beacon in our sky, is not the unmoving anchor of our world, but a traveler, racing through the galaxy with its family of planets trailing behind in a vast, spiraling current. The planets we once imagined as perfect spheres glide not in smooth circles, but in warped, tilted ellipses, tugging on one another, whispering gravitational secrets that ripple across millions of years. We used to think the space between them was silent emptiness. Now we know it hums with invisible forces, solar wind, magnetic fields, cosmic rays, and dust left over from the solar system's violent birth. We used to think the planets were immutable. Now we see them as evolving worlds, scarred by collisions, shaped by time, and constantly remade by cosmic weather. Even the boundaries we once drew around our solar system have dissolved. The neat textbook ending at Pluto has been replaced by the reality of a vast, icy wilderness extending billions of kilometers beyond. The Kuiper Belt, the scattered disk, the Oort cloud. Out there, the sun's gravity grows faint, and other stars begin to tug at its edge. The solar system doesn't end. It fades, blending into the galaxy like a shoreline into the sea. And what's perhaps most humbling of all is that our exploration, for all its triumphs, has barely touched the surface of what's out there. We've visited only a handful of planets with robotic emissaries. We've orbited fewer still. We've landed on even fewer. We've never drilled beneath Europa's icy crust, or walked on the dunes of Titan, or stood beneath the methane rain that falls on another world. We've never sent a probe to Uranus or Neptune since Voyager 2 passed them decades ago. And their mysteries remain frozen in time. Their weather, their storms, their moons, still whispering from the dark. Even now, astronomers are finding hints of something massive lurking beyond Neptune, a possible planet 9, 10 times the mass of Earth, circling the sun so far away that it would take thousands of years to complete a single orbit. If it exists, it would mean that our solar system, the system we thought we had catalogued in full, still hides an entire world we've never seen. Imagine that. After centuries of exploration, there may still be another planet waiting in the darkness. And beyond that, the Oort cloud, stretching halfway to the nearest stars, a region so distant that not one spacecraft, not even Voyager, has come close. We know it's there from the comets it sends our way, but we've never seen it. The boundary between our sun's realm and the galaxy is still theoretical, still invisible, still waiting to be touched. The biggest lie, then, isn't just that our solar system is static or simple. It's that it's finished, that we've somehow completed the map. Because every time we think we've reached the edge, the universe reminds us that the edge doesn't exist. It just moves farther out. Think about how much has changed in only a few generations. When your grandparents were born, Pluto had just been discovered. When your parents were young, we'd never sent a probe beyond Mars. When you were born, no one had ever seen Pluto up close. We didn't know it had mountains taller than the Rockies or glaciers made of nitrogen. And now, in just a few decades, we've watched New Horizons fly past it, seen geysers erupting from Enceladus, found organic molecules on Titan, discovered water beneath Mars, and detected hundreds of planets around other stars. We now know that solar systems like ours are not rare. They're everywhere. But here's the irony. As we discover thousands of exoplanets circling distant suns, we realize how little we truly know about the one system we actually live in. We've glimpsed Earth-like planets hundreds of light years away, but haven't even fully explored our own backyard. And perhaps that's the most important revelation of all. Knowledge doesn't end with discovery. It begins there. Every time we peel back one layer of the solar system's mysteries, we uncover a dozen more. The moment we think we've found the truth, the universe shifts the goalposts. In that sense, our solar system is more than a collection of planets, moons, and rocks. It's a living lesson in humility. It's a reminder that certainty is the enemy of wonder, and that the greatest mistake we can make is to think we've figured it all out. The cosmos rewards curiosity, not complacency. The moment we stop questioning, the story stops growing. We once thought comets were harbingers of doom. Now we know they may have carried the seeds of life. We once thought Pluto marked the end of everything. Now we know it's a doorway to an entire realm of unseen worlds. We once thought the solar system was stable, precise, unchanging. Now we know it's dynamic, fragile, and endlessly shifting. Every lie we've uncovered, every comforting oversimplification, has given way not to despair, but to awe. Because the truth, even when it's chaotic, is always more beautiful than the myth. The solar system is not a completed clock. It's a living organism, pulsing, evolving, and in conversation with the galaxy around it. The sun breathes solar wind into the void. The planets pull and push one another in endless gravitational conversation. Comets come and go like messengers between epochs. Everything influences everything else. It's a cosmic symphony that never plays the same tune twice. And we, fragile creatures of carbon and curiosity, orbiting one small planet around one ordinary star, are part of that music. We were born from the same dust that built the worlds, the same matter that forged the sun. The iron in our blood was once the heart of a star. The water in our oceans may have come from ancient comets. When we look up at the night sky, we're not staring into the unknown. We're looking into our own origin story, written in starlight. So, what is the biggest lie about the solar system? It's the idea that it's a thing to be known, something finite, finished, and understood. The truth is infinitely more inspiring. Our solar system is alive with mystery, and every question we answer only deepens the wonder. The universe doesn't reward finality. It rewards curiosity. It rewards those who dare to look again, to ask again, to imagine again. Because maybe the most beautiful truth of all is this: the more we learn about our solar system, the less we realize we actually know, and the more magical it becomes. The solar system isn't a closed book. It's an unfolding story, and we are living in the chapter where we finally begin to read between the lines. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.